The method that is used to simplify heat conduction calculations uses an analogy with electrical conduction. In schematic form, we can think of heat conduction through a block as being analogous with the conduction of electricity through a resistor. In the case of heat conduction, heat in watts flows through the block, while in the case of electrical conduction, current in amperes flows through a resistor. The resistance to the flow of heat in the heat conduction case is equal to the thickness of the block, divided by the thermal conductivity, times the cross-sectional area. The heat conduction resistance has units of Kelvin per watts. In the electrical conduction case, the resistance to the flow of electricity is the rated electrical resistance of the resistor in ohms. The driving potential that pushes heat through the block is the temperature difference between the two block sides, in the case of heat conduction. In electrical conduction, on the other hand, the driving potential is the voltage difference across the resistor. In equation form, in heat conduction, the heat transfer rate is equal to minus delta T divided by the heat conduction resistance. In electrical conduction, the current is equal to the voltage divided by the electrical resistance. When the same heat flow rate passes through several thermal resistors, the thermal resistors are said to be in a series arrangement. In the shown figure, we have three thermal resistance layers that are placed in series, with a heat flow rate Q dot passing through all of them, and a temperature difference delta T equal to T2 minus T1 across all of them. We can represent the above figure using a circuit diagram as three resistors placed in a series, with a current Q dot flowing through them, and a potential difference delta T across all of them. The total thermal resistance of this series arrangement is simply equal to the summation of the resistances of all the thermal resistors that are in the series. Hence, for the shown case with three thermal resistors in a series, the total resistance is equal to R1 plus R2 plus R3. Note that when using Cartesian coordinates, the cross-sectional areas of the various resistors must be the same, and the sides must be well insulated, in order for the assumption of one-dimensional conduction to be valid. When the same temperature difference exists across several thermal resistors, the thermal resistors are said to be in a parallel arrangement. In the shown figure, we have three thermal resistance layers that are placed in parallel, with the same temperature difference delta T across each one of them, and a heat flow rate Q dot that is divided up amongst them. We can represent the above figure using a circuit diagram as three resistors placed in parallel, with a current Q dot divided between them, and a potential difference delta T across each one of them. The total thermal resistance of this parallel arrangement is equal to the summation of 1 over the thermal resistance for all the thermal resistors that are in the series, all raised to the power minus 1. Hence, for the shown case with three thermal resistors in parallel, the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, all raised to the power minus 1. For parallel resistances, in order for the one-dimensional conduction assumption to be valid, there should be enough insulation between the thermal resistance layers to prevent heat transfer perpendicularly to the main direction of heat propagation. When two relatively smooth solid parts come in contact together, the actual contact area between them can be much smaller than the apparent contact area between them, due to the roughness of their mating surfaces. The apparent contact area is simply the mating area between the two objects that we can see with the naked eye. The actual contact area is where the surface roughness elements of both objects actually touch each other. The majority of the space between the mating surfaces is filled with ambient fluid, which in most cases is air. Even though the gap is small, since air has low thermal conductivity, the thermal resistance of the gap is usually large enough not to be negligible, as compared to the thermal resistances of the mating objects. The total thermal contact resistance has the same units as the heat conduction resistance, or Kelvin per watt, and is written as capital R, subscript T, C. The total thermal contact resistance is equal to minus the temperature drop across the interface, divided by the heat flow rate through the interface. The reason for the minus sign is that, similar to one-dimensional thermal conduction, the temperature decreases in the direction of heat flow. The thermal contact resistance of a unit area has units of meters squared Kelvin per watt, and is written as small r, subscript T, C. The thermal contact resistance of a unit area is equal to the total thermal contact resistance times the apparent surface area of the interface through which heat is flowing. It is also equal to minus the temperature drop across the interface, divided by the heat flux through the interface. The thermal contact resistance exhibits itself as a sharp temperature drop across the interface through which heat is flowing. For the thermal contact resistance, using the equation of the heat diffusion rate, we find that the change in temperature across the interface is equal to minus the heat diffusion rate times the contact resistance. Hence, for a constant heat diffusion rate, as the contact resistance increases, the absolute value of the temperature drop across the interface increases. Furthermore, if we fix the contact resistance, then as the heat diffusion rate through the interface increases, so will the absolute value of the temperature drop across the interface. For the thermal conduction resistance, using the equation of the heat diffusion rate, we find that the derivative of the temperature with respect to the distance x, or in other words, the slope of the temperature versus x curve, is equal to minus the heat diffusion rate, divided by the thermal conductivity, times the cross-sectional area through which the heat is flowing. Hence, for a constant heat diffusion rate and cross-sectional area, as the thermal conductivity increases, the absolute value of the slope of the temperature curve decreases. Thus for a constant heat diffusion rate and cross-sectional area, and for the same thickness of material, the absolute value of the temperature difference across the object is smaller for a good conductor as opposed to an insulator. We thus conclude from the shape of the shown temperature versus x curve, that the thermal conductivity of the material on the left side of the curve is higher than the thermal conductivity of the material on the right side of the curve. Thermal contact resistance will exist whenever heat is conducted between two distinct objects. However, the contact resistance can be reduced, or even eliminated, using the following factors and practices. By fusing the two objects together, either directly, or using an intermediate filler material by means of welding or soldering, the air gap between the two objects, and hence the thermal contact resistance between them, can be eliminated. By making the mating surfaces smoother, the effective contact area can be increased, while reducing the air gap within the interface. This will tend to reduce the contact resistance of the interface. Furthermore, the higher the pressure that is exerted on the interface, the more the small surface roughness asperities of that interface are flattened out, which also tends to increase the actual contact area, and hence reduce the contact resistance. Finally, the space between the two mating surfaces can be filled with a highly conductive compound that replaces the air gap between them, and hence greatly reduces the contact resistance.